Hi there everyone, my name is Sally and I am a mechanical engineering student at the University of Maryland College Park. This semester I built a portable LIDAR sensor. Now I'm really excited to show you and tell you all about what I've done, but before we do that, let's get some background info. First off, what is LIDAR? LIDAR stands for Light Detection and Ranging, LIDAR. Some really nice LIDAR sensors are able to sense the depth of water, guide autonomously driving vehicles, and quantify biomass in areas. Now, the way this project came about is from a course taught by Dr. Steve Mitchell at the University of Maryland. I had the privilege of taking his course ENME 489Y, or Introduction to Remote Sensing, this past semester. The course is built around exposing students to different types of remote sensing, mainly LIDAR and its forms, and a little bit of computer vision. During this course, we were guided in creating our own portable LIDAR sensor and told to go out onto campus, pick an object, and scan it, create a clean 3D point cloud of an object that would fit inside a 6-foot square box. The target I chose on campus is someplace very near and dear to my heart. It's a bench. But not just any bench. This bench is located behind the engineering building I've probably spent the most time in the last 4 years, and also has a beautiful view of my favorite tree on campus, Martha. Martha is a royal Japanese cherry blossom, and I knew I'd be spending a lot of time there, so I wanted to make sure I had a good view. Before we get into the nitty-gritty of my LIDAR design, it makes sense to talk a little bit more about remote sensing. LIDAR is a type of remote sensing, a science and technology that allows for the obtaining of information about an object without direct contact with said object. In remote sensing, information is carried through some kind of remote interaction, usually a form of radiation. A radiation signal of known property hits the target, and then the return radiation is picked up by sensors. The changes in the radiation carry information about the object being sensed. There are two types of remote sensing, active and passive. Passive remote sensing depends on naturally occurring radiation, sunlight or night glow, for instance. Active remote sensing depends on a self-generated radiation signal, light, radio, micro, or sound waves. LIDAR sensors are active sensors, and along with that active signal they're sending out, they also have a couple other things on board, GPS and IMU. GPS is Global Positioning System, and IMU is Inertial Measurement Unit. Now let's talk about my LIDAR. Here are some key sensor aspects. 3D printed chassis, tripod, battery pack, Arduino that powers my line laser, which is going to be my radiation, my Raspberry Pi camera and Raspberry Pi, which are my receivers, my phone is my GPS and IMU, my computer for my data acquisition system, which is hooked up to my Raspberry Pi via hotspot and virtual network connection. This LIDAR sensor uses the geometrical LIDAR technique. The laser shoots out, hits the target, and that transmitted signal is received by the Raspberry Pi camera. The images I take on the camera are run through my data acquisition system, or DAC, which is my computer and some Python program, to detect the location of the beam as it scatters off the target. The DAC intensifies the pixels that correspond to the laser and uses the XY coordinates of the pixels to compute a range measurement based on the sensor's geometry using computer vision. The angle measurement from the IMU, which is my phone, lets me calculate the vertical distance of each point. This geometrical triangulation method using a Raspberry Pi and OpenCV is very concisely explained by Todd Danko. The link to his website and this page is in the description. Before I could go onto campus to scan my object, I had to calibrate my sensor. By changing different values in my Python code, I was able to get a better fit for my line laser, figuring out where an accurate range measurement was according to my images that I had taken. As you can see, different values gave different best fits. I decided to go with the best fit for the further range and then scan accordingly. Once I had calibrated my DAC, it was time to head out and scan my bench. Like I said before, I used VNC to connect my Pi to my laptop via my hotspot, then ran the code that took the picture on the Pi, named the picture from the IMU angle that I read off of my phone. I ended up taking scans from 7 separate positions so I could fully capture my target. Some features of my target that made it kind of difficult to scan were the wall, the seat in the back, and the dark base pillars. The wall kept me from being able to get a straight-on shot at the back of the bench. The seat and the back of the bench are in two different planes. It's easy to scan the back of the bench, but not as easy to scan the seat. The dark base pillars have a different coefficient of reflectivity, so I knew I had to account for those somehow in my data processing. The bench was also very long, so I decided to split it up into 3 separate sections in the front. I then took those 3 separate scans and split them into bench wood and paste pillars. That way I could make different hue, saturation, and value filters to change how my LIDAR would pick up the red color of my laser. In addition to 3 scans from the front, I also captured both ends of the bench and then from oblique angles in the back left and the back right, so that way I could capture the back of the bench as well. Once I had finished scanning, it was time to process my data. The first step was doing a sort of ugly pre-filtering with Microsoft Paint. It wasn't elegant, but it worked to remove a lot of the excess red. The next step was to create HSV filters for each set of scans using OpenCV in Python. I ended up making 11 different filters total. The next step was to generate the data using the geometrical LIDAR technique using OpenCV and Matplotlib. This outputted a .txt file for each set of data. I then took those .txt files and run them through MATLAB to create matrices that I could then edit. Within MATLAB, each dataset was able to be rotated and translated, so that way it matched up with the other points. I then took those matrices that were matched up and used the cat function, which concatenated them together. The last step was to trim the cloud. Excess points that looked like they were superfluous or outside of the range of what I could expect were removed. The filtering really does make a difference. Here is the 3D point cloud without the filtering. And here's the 3D point cloud after filtering. So how does this scan compare to the actual bench? Well, the actual bench is 35 inches high, 2 feet deep, and about 80 inches long. This scan shows that the bench is 18 inches deep, 38 inches high, and about 50 inches long. The biggest error is in the length, and I really think that's a stitching error between my left, middle, and right scans. But besides that, we're within about 6 inches of error, so not too bad. Just for fun, I tried generating an object out of my 3D point cloud. I brought the .txt into MeshLab and then tried to clean up the point cloud just a little bit more before meshing all of the edges together. Yeah, big oof. So there we are. That's the whole thing. We went from solid object to sensor to 3D point cloud and then to something like a mesh. I'd like to thank the Academy, Dr. Mitchell, and Google for this project. Hope you learned something. I know I learned a lot. Bye.